Welcome to today's class. The topic of today's lecture is design of two-way slab. Under this topic, if we visualize a slab resting on supports having a longer span Ly and a shorter span Lx, and if we take a span ratio Ly by Lx, if the value comes lesser than or equal to 2, only then this slab would become a two-way slab. But in two-way slab, there are development of strips along the edges of the slab. So along Ly, the strip on the left side is Ly by 8 and the strip on the right side is Ly by 8. But the central length between these two strips is 0.75 Ly. Similarly, along Lx value, the short span, the edge strips width is 1 by 8 Lx and again 1 by 8 Lx. So you can see here all along the four edges of the slab there are edge strips having a specific width, and the central portion of the slab which is left out is known as middle strip, that is the 0.75 Ly in this direction along Ly and 0.75 Lx in Lx direction. So with this, if we further think that what is the influence of deflection in the slab and the bending characteristics. So if we say take out a simply supported slab, a slab simply resting on the four walls, then under the influence of the external load, the bending moment, the slab would bend like this. The shorter span is bending and the longer span is also bending here, and this bending takes place simultaneously, and because of this a slab is deflected as it is seen in the image. But in case of one-way slab, the bending takes place in only one span, and if a one-way slab, just like a slab over a corridor, a longer slab where the Ly by Lx is more than 2, then simply one span, that is the shortest span, would bend and it would like this. So clear-cut difference is visible in these two images, that what is the difference of deflection, the bending in case of two-way slab and one-way slab. So if you say the restrained slab case, the middle of the slab would be a middle strip and all along this would be taken as edge strip. So if we see further that what is the restrained slab bending nature, so in restrained slab means the corners of the slab would not lift as it is lifting in case of the simply supported slab. It would be in touch of the support, but where the edge strip would be undergoing an upward curvature, that is the hogging bending on along all edges, and the middle strip, the central portion of the slab, would go on downward curvature, that is the sagging bending. So there is a difference of bending nature in edge strip and middle strip. If it is a restrained slab, it means the slab corners cannot lift and the support would having a opposite type of nature of the slab than the open span of in the middle strip. Now to begin with the design of the two-way slab, the first step we have to carry out is the effective depth calculation, followed by the load calculation, effective span calculation, bending moment calculation, checking the depth in flexure, then calculation for the area of the main steel, then checking the slab for cracking, and finally to draw a reinforcement sketch. To follow all these steps, we have taken a numerical problem. So the statement of the problem is design a simply supported two-way slab having size 3 meter by having size 3.5 meter by 3 meter, clear spans supported on 300 millimeter thick walls on four sides. Take imposed load 3 kN per square meter, floor finish 1 kN per square meter. Take M20 concrete and Fe415 steel. So with this dimension of the slab, if you calculate the span ratio Ly by Lx, that is 3.5 by 3, that is 1.166 less than 2. So because it is less than 2, so it is a type of two-way slab. Now the first step is the effective depth calculation. So as per IS 456-2000 page 39 for Fe415 steel grade, the actual span is 3 meter, which is less than the allowed span 3.5 meter, so it is okay. Similarly, the actual loading class is 3 kN per square meter, which is less than the allowed loading class 3.5 kN per square meter, so it is okay, also okay. Then as per page 38 figure 4, for assumed percentage of 0.3% steel as per deflection control criteria, the ratio of span to effective depth, that is Lx by d, is 35 into modification factor into 0.8. And in case of this type of percentage assumed of steel area, from figure 4 we get the modification factor 1.45. So 35 into 1.45 into 0.8 comes 40.6. So from this we can calculate a small d, the effective depth value of slab, that is the Lx 3000 millimeter divided 40.6 is 75 millimeter. So by using this small d, we can calculate capital D, the overall depth of the slab, that is small d plus 10 by 2, the assumed bar diameter is 10 millimeter, plus 20 millimeter, the nominal clear cover of the slab, that is the gap between the bottom of the steel reinforcement and the bottom of the slab, that is 75 plus 5 plus 20, and this way it comes 100 millimeter. So we have now the small d as well as the capital D for this slab. Now the second step is the load calculation. If we calculate the dead load, that is for given capital D 100 millimeter, it comes 0.1 meter, multiply the design width of the slab 1 meter, multiply 25 the density of the RCC, and this way we get 2.5 kilonewton per meter. The floor finish given is 1 kilonewton per square meter, multiplied by the design width of the slab 1 meter, so this way we get 1 kilonewton per meter. The live load given is 3 kilonewton per square meter, multiply the design width of the slab 1 meter, and we get 3 kilonewton per meter. So adding all these three, we get total load 6.5 kilonewton per meter. So to calculate the factored load for design calculation, we multiply this total load by 1.5, the partial safety factor for load, and finally we get the factored load 9.75 kilonewton per meter. So this way we have now the total UDL, uniformly distributed load, W per meter run, is 9.75 kilonewton per meter for the entire slab. Now the second step is the calculation for the effective depth of effective span, that is L. So as per IS 456/2000, page 34, clause 22.2a, along shorter span we will first calculate the effective span, that is equal to Lx plus d, that is 3000 millimeter Lx plus 75 small d, so 3075 millimeter. And the second option is the center to center of supports, that is Lx plus width of the wall, and this is 3000 plus 300, the width of the wall, that is 3300 millimeter. So smaller of these two value is 3075, which is taken as effective span in the short span case. But along longer span, if you find out the effective span, that is Ly plus d, that is 3500 millimeter, the longer span, plus d here comes 75 minus 10, that is the two layer of bars will come, so minus 10 mm diameter bars, so minus 10, that is 3565 millimeter. Center to center of supports, that is Ly plus W, 3500 plus 300, that is 3800 millimeter. So the effective span along longer direction is 3565 millimeter. So we have now both the spans effective span value. Now finally we can calculate the bending moment. So as per IS 456/2000, page 91, table 27. So in case of two-way slab, we have to calculate bending moment coefficient along shorter span alpha x value and along longer span alpha y value. But for this we need Ly by Lx ratio for effective values, that is 3565 by 3075, 1.15. So this comes in between 1.1 and 1.2. So in between, by interpolation, we get alpha x 0.0799 and alpha y 0.0601 for simply supported two-way slab case. By using this, we can calculate the bending moment mx along shorter span, alpha x into w into Lx square. So putting the values, we get 0.0799 into w 9.75 into Lx square, that is 3.075 square, and this way we get 7.366 kilonewton meter. Similarly, along longer span, the bending moment is my equal to alpha y w Lx square. So 0.0601 into 9.75 into 3.075 square, and this gate is 5.54 kilonewton meter. So from this two values of the bending moment, the higher one is 7.366 kilonewton meter. For this higher bending moment values, we would check the slab for flexure and calculate the effective depth again. So as per SP 16, page 10, table C, the given equation for mu limb, that is the limiting value of moment of resistance 0.138 FCK BD square for Fe415 steel grade. So putting all the values in this, we can find out a small d, that is the effective depth from flexure equation, that is d equal to root under 7.366 into 10 to the 6 divided by 0.138 and 20 and 1000. So all this gives us small d equal to 51.66 millimeter. So this depth is less than the adopted value, that is 75 millimeter, as we have used in the previous slides. So it is also okay. Now to calculate the main steel area, that is AST. So as per SP 16 table 2 for M20 concrete grade, we need to calculate mu by BD square. So along shorter span, that is LX, mu by BD square comes 7.366 into 10 to the power 6 divided by 1075 square. So this gives a ratio of 1.309. So by using this ratio, we calculate from table 2 the percentage of steel in tension, that is PT 0.395%, and by using this percentage the AST comes 0.395. AST is equal to PT multiplied by BD divided by 100. So putting the values, we get 0.395, 1000 into 75 by 100. So this way we get 296.25 millimeters square. So if we assume here a 10 millimeter diameter bars to be provided as main steel, so the spacing between bars would come 78.5 into 1000. 7.5 means the 1 bar diameter area into 1000 divided the total calculated area 296.25, and this way we get the value of spacing 264.97 millimeter. So provide 10 millimeter diameter bars at the rate of 264 millimeter center to center along the shorter span. Now along the longer span, similarly we can calculate mu by BD square, and mu by BD square comes 5.54 in 10 to the power 6, that is the MOA value, divided by 1000 into 65 square. The effective depth ratio in case of longer span is 75 minus 10, the bar diameter, and this way we get this ratio 1.311. So the PT values, that is the percentage of tensile steel, comes 0.3957%. So with this percentage we can calculate AST 0.3957 into B into D, 1000 into 65 divided by 100, that is 257.2 millimeters square. So if we assume 10 millimeter diameter bars as main steel, the spacing of bar would be 78.5, 1 bar diameter into 1000 divided by 257.2, and it gives 305 millimeters center to center. So we can provide 10 millimeter diameter bars at 305 center to center along longer span as a main steel. Now the next step is to check the slab for cracking. Cracking means check the slab for a spacing between two bars. So as per as 456 2000 page 46 clause number 26.3.3b, the value given is the spacing should be 3D, 3 times effective depth, that is along LX it comes 375, 3 into 75, that is 225 millimeter, and along LY it comes 3 into 65, 195 millimeter. Now the maximum allowed value is 300 millimeter only. Along LX it is 300, and same value along LY. Now the calculated spacing is for LX 264 millimeter and for LY 305, that is the longest span. So a smaller of these values along LX is 225 millimeter, and along longer span LY is 195 millimeter. So we can provide this spacing by using 10 mm diameter bars as per the cracking conditions. Now the last step is to draw reinforcement sketch. So if you remember by any construction site where the top of the slab before casting is covered with a scaffolding, that is the centering wooden planks are used. So you can assume the bronze surface is the top of the scaffolding used before the construction of the slab before casting. So over the surface we place the reinforcement. So here one line means the pink line shows a reinforcement bar is coming from this support and extending here to this support by a distance of, this is LY, so LY by 7, as it is a simply supported slab, so it is LY by 7 distance, and from there it starts bending up, it goes up. So similarly alternate bars, that is the spacing given in in this ly is 305, so this spacing would come 305 into 2 at double spacing. Alternate bars are coming from this way, from this support extending to the front support line. So the next line of reinforcement will come from, suppose in this direction along Lx. So it is coming from this way, coming to up to a distance of Lx by 7, and then it starts going up, and the arrangement is again at the double strip from the starting of the slab from front to back, and all bars would take its position like this. Similarly, the bars, alternate bars is coming from this side, so again it goes up to a distance of Lx by 7 from this support, and it go to start going up, that is the bent up bars. So this way all along the four edges of the slab, various bars would be arranged, placed. All intersection of the two bars would be tied with the reinforcement fine whites, and you can see here that one bar coming from this end bent up in this area on the top of the support, and the next bar coming from this end and bent up in this area. So similarly, by starting a bar from one support and bent up at the neighboring support, so this way the all edge strip of the slab would be provided with the bent up bars. But in the middle strip area, you can see here that the dotted line, all the bars are near the bottom of the slab. So this is the mesh formed near the bottom of the slab, but near the top of the slab in the edge strip, so 50% of the steel bars of the middle strip is provided at the top of the slab as bent up bars, and 50% of the bar is again at the bottom of the support. So you can see here the pink bar at the bottom of the support, and this is the yellow bar is at the top of the supports. So the distribution of bars takes place in the edge strip, and 50% as bent up and 50% is going continuously to the bottom of the bottom area of the slab near the supports. So this way the slab reinforcement in plan can be arranged and placed. But now if we take cross section XX and cross section YY, then the reinforcement arrangement in cross section is like this. Suppose here the red bar is coming from the right support going to Lx by 7 up to this point, and then it goes up. So red bar is here, you can see it coming from the right and going bent up on the left. The black bar is coming from the left and going up to Lx by 7 distance from the right support, and then it starts bending up. So this is the black bar and bent up on the right supports. The pink bar and the yellow bar are the bars along the Ly span. When we cut the section at along XX, then these bars will be visible as a cross section, as a circles, and these circles are visible in this cross section. So the designation for the bars are written on the cross section. The main steel area along shorter span is 10 mm diameter bars at 2 to 5 mm center to center, but the 10 mm diameter bars at 195 center to center is provided here, that is along longer span and shown here as circles, and it is the pink bar as straight bars in the plan. So when it is bent up, then this space is doubled. So 10 diameter bar 450 mm center to center is as bent up bars on this support, and similarly at on this supports. So both yellow and both red and black bars are having this spacing. Similarly, both pink and yellow bars are having this type of diameter and spacing. So if we discuss this the cross section along XX section, then again along LYY section we can draw the similar cross section, but the only difference between these two cross section is that the main steel along XX, that is the shorter span, is nearest to the bottom of the slab in the middle strip, you can see here, but the same bar is here as a cross section, that is a circle again, but the nearest to the slab, and the longer span bar which was visible here as circles, it has been shown here as straight lines because it is visible along the longer cross section. So this is the circles, that is the red bar in Lx span is visible here as circles, So again, to designate the slab reinforcement, we have to write their diameter bar and a spacing. So this way we have two cross sections, one along shorter span XX and one along longer span LY section. Now to picturize it more, if we draw a three-dimensional picture, I have tried to clarify how bars are arranged in the slab. So if we see the similar cross section on longer span, and it is having a top bars in this area, then it is in the top in this area. You can see here these top bars would in cross section would be visible in the plan like this in the edge strip, that is the bent-up bars. Similarly here the bent-up bars in the that is the top portion of the slab, and this is visible in the plan like this. So all bars in this bent up is in the plan also. Similarly in the shorter span, here it is the bent up bars red and this side. So these all bent up bars are visible in this area. Similarly the bent up bars in this area on the top of the slab. Now the central zone where the slab is having the bottom bars, so this bar that is bent up which goes to the slab, bottom of the slab and up to the end of the supports. Similarly from other direction the bottom bars comes, that the bent up bars starts in the bottom of the slab. So the mesh of the bars formed in the bottom of the slab in the middle strip and the mesh of the bars formed in the edge strip are visible, and in the actual slab construction, if you visit in a site, you will see that the bars reinforcement along the edges of the slab are similar to this image, and this gives us a better understanding of the slab reinforcement, the placing of the reinforcement, the dimensions, where the bent up should start in case of simply supported slab, and how it should be tied, and what is the precautions to be taken for a safe exact casting of the slab, and the proper location of the reinforcement needs to be ensured by fixing them at all junctions. So with this, thank you very much for patiently listening to this lecture. So by this lecture we learned what is basic deflection patterns of two-way slab, what are the design steps of two-way slab, and we have solved out, designed a simply supported two-way slab case and discussed their reinforcement sketch. With this, thank you very much.